Hello and welcome to today's lesson on beta minus decay. Today we will distinguish between the two kinds of beta decay and their properties. Then we will learn how to write nuclear equations for beta minus decay. So far we have explored the basic atomic model and the fundamental nature of radioactive decay. With this background, we can now delve deeper into beta minus decay. This lesson will broaden our understanding of nuclear processes, illustrating another way in which unstable nuclei achieve stability and transform into different elements. Beta minus decay is a type of radiation where fast-moving electrons, referred to as beta particles, are emitted from an unstable nucleus. One important thing to note is that the beta particle is not an electron from the atom's outer electron cloud. Instead, it is generated inside the nucleus and then released. Beta decay happens primarily in neutron-rich nuclei. These are atomic nuclei that have too many neutrons compared to protons. Inside the nucleus, a neutron is converted into a proton and an electron. The electron, now known as the beta particle, is emitted from the nucleus at high speed. This emission helps the nucleus become more stable by balancing the ratio of neutrons to protons. The newly formed proton stays inside the nucleus, which increases the atomic number of the element by 1. This means that the atom transforms into a different element, one with a higher atomic number. Note that the mass number remains unchanged. This is because even though a neutron has turned into a proton, the total number of nucleons, protons and neutrons, remains the same. Beta particles are much lighter than alpha particles and carry a single negative charge. Because of their small mass, beta particles move much faster than alpha particles. Those properties greatly impact how beta particles interact with matter, as we will explore in an upcoming lesson. Now that we understand what beta minus radiation is and why it occurs, let's see how we can represent beta minus decay using nuclear equations. To remind you, a nuclear equation represents the changes that occur within the nucleus during radioactive decay. It ensures conservation of both mass number and atomic number. Let's take carbon-14 as an example. We begin by identifying the initial nucleus. The carbon atom has a mass number of 14, which is the total number of protons and neutrons. Its atomic number is 6, the number of protons. During beta minus decay, a neutron in the carbon-14 nucleus is converted into a proton and an electron. The electron, which is the beta particle, is then emitted from the nucleus. The next step is to consider mass and atomic number conservation. The mass number remains the same at 14 because a neutron is converted into a proton, so no mass is lost or gained. However, the atomic number increases by 1, changing from 6 to 7, because the nucleus now has one more proton. With this information, we can now identify the new nucleus. The increase in the atomic number by 1 means the new nucleus has an atomic number of 7. Referring to the periodic table, the element with an atomic number of 7 is nitrogen. Thus, the new nucleus is nitrogen-14. Now we can show the representation of beta minus decay. In nuclear equations, the beta particle is represented as shown on the whiteboard. The symbol E indicates it is an electron, the subscript -1 represents its charge of -1, and the superscript 0 indicates its negligible mass compared to protons and neutrons. When written out, it should look like this. C14 becomes N14 plus a beta particle or an electron. Let's try another problem. We need to write the beta minus decay equation for phosphorus-32. We start by identifying the initial nucleus and its properties, which is phosphorus-32, with an atomic number of 15. Then we determine the changes after emission. When phosphorus undergoes beta minus decay, a neutron is converted into a proton and an electron, the beta particle. The mass number will remain the same at 32, but the atomic number increases by 1. So 15 plus 1 equals 16. Now we can identify the new nucleus. The element with an atomic number of 16 is sulfur. Therefore, the new nucleus is sulfur-32. When we write this as a nuclear equation, its P32 becomes S32 plus a beta particle. Let's try our final problem. We need to write the beta minus decay equation for iodine 131. As previously, we first identify the initial nucleus and its properties, which is iodine 131, with an atomic number of 53. Next, we determine the changes after emission. When iodine 131 undergoes beta minus decay, a neutron is converted into a proton and an electron, beta particle. Therefore, the mass number remains the same at 131, but the atomic number increases by 1 from 53 to 54. Now we can identify the new nucleus using the periodic table. The element with atomic number 54 is xenon. Therefore, the new nucleus is xenon 131. We can now write the nuclear equation as iodine 131 becomes xenon 131 plus a beta particle or an electron. In today's lesson, we delved into the properties and formation processes of beta minus radiation. We learned that beta minus decay involves the emission of a beta particle, which is a fast-moving electron, a process that occurs primarily in neutron-rich nuclei, where a neutron is converted into a proton and an electron. We understood that the atomic number of the element increases by 1, while the mass number remains unchanged, and illustrated this in practice using nuclear equations. In summary, today's lesson provided valuable insights into the nature of beta particles, the reasons behind beta minus decay, and the method of representing this process through nuclear equations. This knowledge broadens our understanding of radioactive decay and the behavior of unstable atomic nuclei.